All right, so this is the practice longitudinal waves page. So the first question says, what kind of wave is pictured? So they're talking about this wave. So we know that this type of wave is a longitudinal wave. So far we've learned about two different types of waves. We've learned about transverse waves, which are the up and down waves, and then we've learned about longitudinal waves, which are the side-to-side waves. Number 2 says, give 2 real-world examples of this type of wave. So one real-world example would be sound waves. Earthquakes would be another one. Slinkies, we use slinkies. Now, slinkies, remember, it's the ones that are going to go side to side. We're not moving them up and down. Those would be transverse. But if we move the slinky side to side, then it would be a real-world example of a longitudinal wave. Number 3 says, label the compression, the rarefaction, and the wavelength on the picture. All right, so our compression, we know that the compressions are when the particles are very tightly packed together. So this right here is our compression. For our rarefaction, we know rarefactions are when the particles are spread apart. So this section right here is a rarefaction. And then it says, and wavelength on the picture. So with a longitudinal wave, compression to compression is a wavelength. But we could also measure from rarefaction to rarefaction being a wavelength as well. And remember, I put the little Greek symbol for lambda up here to show the wavelength, because remember, this symbol is what we use to symbolize the word wavelength, and that's lambda. So I've labeled my compression, which is the close particles. So I've got 3 compressions. And it says label the rarefactions. I've labeled the rarefactions, and then the wavelength, which is compression to compression or rarefaction to rarefaction. Number 4 says, what is amplitude a measure of? So amplitude on longitudinal waves and transverse waves is a measure of the energy carried by a wave. Remember that amplitude is always going to be the same, no matter if it's a transverse or a longitudinal wave, is always the measure of how much energy it's carrying. Even though we measure them differently, it's going to on both waves. The overall idea or definition of amplitude is the amount of energy carried by a wave. The way we measure amplitude on a longitudinal wave is the density of the compression. So, the way we measure So it's from one side of the compression to the other side of the compression is going to be your amplitude. So this right here is the amplitude. So one side of the compression to the other side of the compression. Remember, we talked about density is how closely packed together the particles are. So the compression is going to have however much the density is of that compression is what the amplitude is. Number 5 says, what do you believe the relationship is between wavelength and frequency? Draw a picture to support your reasoning to show why this relationship makes sense. All right, so yesterday we talked about how frequency is related to wavelength. So frequency is the amount of wavelengths in 1 second of time. So if I say that this is 1 second of time, and I have all of these waves, and then I have another second of time, and this is my waves. On this one, I have very short wavelengths. So I've got lots of wavelengths right here. Very short wavelengths. So that means that I'm going to have a lot of waves in that 1 second of time. So my frequency is going to be very high. So short wavelength, and remember I'm using the symbol for wavelength, which is called lambda, equals high frequency. And that's the symbol for frequency. So this little curly F is the symbol for frequency. So that's the relationship between a short wavelength equals a high frequency. Over here, I've got much longer wavelengths. So I'm going to have a very low frequency. So long wavelengths equals low frequency. Remember this, when we talk about frequency and wavelengths, this one's going back to that story that I told you about how we're standing on a pier at the beach. So we've got our beach waves, and I know those are beautiful beach waves. And we're standing at the end of the pier, and I give you a timer. And when one crest hits the back of the pier, you're going to start your timer. And for 1 second, you're going to count how many wavelengths hit the end of the pier. So for 1 second, we've got 1, 2, 3, and then we stop our timer. And at the end of that 1 second, we count up our wavelengths. So we had 3 wavelengths in the 1 second. That was our frequency. So that's how we calculate frequency, remember? So we've got a short wavelengths. We're going to have a higher frequency because there's more waves that could hit our pier. If we have long wavelengths, it's going to be a low frequency because not as many waves are passing by in that short amount of time. Number 6 says, why would a sound wave travel faster through a solid than a gas? Why can they not travel in outer space, which is a vacuum at all? Explain. All right, so I'm going to break this down to 2 different parts. So the first question and then the second question. So number 1, when we talked about states of matter, we talked about how there are solids, liquids, and gases. The particles in a solid, remember when we talked about how the particles in a solid, they're really tightly packed together and they just kind of vibrate because they're so tightly packed together. And then in a liquid, they're pretty close, but they're not quite as close as a solid and they can slide past one another. And then in a gas, they're really spread apart. And it takes a lot of effort for them to actually hit one another. Do we remember that? So with sound waves, they're going to travel based on being able to hit the next particle. So the closer that next particle is, the easier it is for it to travel. So that is the answer for number 1. In a solid, the particles are close together and can travel much easier because the distance between them is much shorter than in a gas. So when you think about this, I want you to think about like a football stadium. So I'm going to load us up and we're going to go to an Alabama and Auburn football game. And there's going to be, and this is like either before or after COVID, because, you know, football right now, we're having cardboard fans. So we're going to go, and the whole stadium is completely packed, and every single seat is full. And all of a sudden, the waves start. Y'all know what I'm talking about, right? Where people like stand up and throw their arms up, and then they sit back down. And it travels around the whole entire stadium. When people are really tightly packed together in a stadium, you can easily see that wave travel, right? What would happen, though, if I took us to a stadium and there's like 25 of us in here, and it's during COVID, and there's only 25 of us in the entire Alabama football stadium, which is humongous. It holds like hundreds of thousands of people, and there's only 25 of us. How stupid is that wave going to look? It's going to look very stupid, because you're going to be spread out over this humongous entire stadium, and one person is going to stand up and move, and then it's going to take a long time for us to wait for the next person to stand up and move. And it's going to take a long time for the next person to stand up and move. That's exactly how these sound waves move. If they're closer together in these solids, it's going to just travel right across that medium, because it's making the other particle bump together. In a liquid, it's a little bit harder. And in a gas, it's the hardest, because these particles are not very close together. It's going to take a long time for them to bump into the next one to allow that sound wave to travel. Does that make sense to everybody? On the second part, it says, why can they not travel in outer space, which is a vacuum at all? Okay, well, there is no matter in space. There is no medium for it to travel through. So there are less particles than a gas, because there are none. So there is no way for the sound wave to travel, because the sound wave, or the longitudinal wave, has to have particles to move. Well, if there's no particles, then there's no way to move. It would be like watching a wave in a stadium with no people. That would be the worst wave. That would be worse than the one with just our class in the stadium, because you're not watching anything. There's nothing there to move. So no matter in space. So the particles in the wave have nothing to travel.